Okay, good morning, everybody. Welcome to the class. I just want to make some quick notes. I announced this morning, early morning, that next Thursday from 3:30 to 5:30, the time of tutorial would be a normal class, and the week after. So on Thursday, we'll have 3 hours of class. We'll have some break in between. And on Friday, we'll have our normal class. This way we recap because there is possibility first week of March, we will not have classes. And we can repeat this. Sometimes maybe I did it last year for the same. So we finish earlier. So you will have more time for assignment 4 and to do your other courses tasks. Also, I announced today that for those 18 students who are not enrolled yet in any group, if you don't find a group, no action required from your side. I will put you in any group that consists of 4 or 5 students. If you have your own group, please enter it as soon as you can, and I put a due date. After this due date, no group will be accepted. I will assign randomly because we cannot wait more. We need to announce assignments. We need to announce the schedule of assignment and the quizzes by the end of next week, which will be approximate dates. However, we'll try as much as we can to stick with it. If there is a changes, it will be plus or minus a week, not more than that. And as I mentioned, all assignments are due Mondays, 11:55 p.m. Thursday, before that Monday, there will be a tutorial by the TA, carried out by the TA, so he can answer your questions. He can give you some extra question if he wants to clarify some ideas for you guys. Okay, yesterday we stopped here at slide 21. But before that, I just...
Sorry, sir, your notes are on the wrong screen, so we can just see your desktop.
Oh, I see. Now is it okay?
Yes, thank you.
Okay. So now we stopped here yesterday at slide 21. But before that, I need we mention all of these, but I need just to have it in a written form so every student will be aware of this. So when we are talking about deterministic finite automata, and we call it DFA, so a definition: an alphabet is a finite set of symbols denoted by sigma or capital or uppercase of gamma. But normally in this course, we will use sigma. A string over an alphabet is a sequence of symbols from the alphabet. For example, string W that consists of 0, 1, 1, 0, 1. If I have a 2 member on the alphabet in that set, which is 0 and 1. Length of a string, we mentioned that before, or the cardinality, is the number of symbols in the string denoted by W between the 2 columns, or they call it modular sign. So the cardinality of 0, 1, 1, 0, 1 is 5. The empty string is the string consisting of 0 symbols denoted by epsilon. Sigma to the power I for a string W. W is a string over sigma, and the length of W will be I. So when what I'm saying alphabet sigma, if I said 2, that means it consists of 2 symbols. And what are all the possibilities? It's 0, 0, 0, 1, 1, 0, 1, 1. Sigma star, what do we mean by sigma star? Is the set of all possible strings that can be constructed over the alphabet sigma. So sigma star, it's the union of I greater or equal to 0 of sigma I. So sigma naught or sigma 0, it is epsilon. Sigma 1, it will be 1 symbol. Then I will have 1 symbol. Sigma 2, here, if I have 2 symbols. What is the cardinality of sigma 0? Is 0, which is epsilon. When I'm saying sigma plus in some box, that means it is all possible string except the empty string, which is from sigma 1 and above. A language L over an alphabet sigma is a subset of sigma star, or it could be sigma star itself. For example, if we have two symbol, this is the sigma star for two symbol. Back to DFA, we said if we have a language that consists of W ends with a 1. And we consider that the language are 0, 1, binary digit. Construct a DFA that accepts all string are in this language. As we said, we have to put the start, and in some drawing, they don't write the word start, just the arrow. The arrow itself means that here is the start. If you put a start, you don't put a start, it's up to you. I put it for a clarification. But if you just put the arrow, that means we begin here. Okay, so Q note, we start. So if we have 1, in this language, either we receive 0 or we receive 1. So as per our strategy that we mentioned earlier yesterday, what do we mean? How many states do I need? 2 states. Initial state and final state or accept state. So Q note, if I receive 0, I will stay in the same state. If I receive 1, because here we need to be end by 1. So if I receive 1, I'll go to Q1, which is the final state and accept state. How many I repeat the 1, I will stay in the same state. But if I get 0 again, I'll back to Q note. So the formal definition of DFA as we get it yesterday is a 5-element tuple, Q, capital, sigma, small or lowercase of delta, Q note, and F, where Q is a finite set of states, sigma is the alphabet, delta is the map between Q and sigma, and it should belong to Q as an output, is the transition function. We call it a transition function, which will map between one state and another or the same state. And all here, what is a Q in this question? It is Q naught and the Q1. Those are the states that will form the Q. Q naught should belong to Q, is the start state. F is included or equal to Q, is the set of accept state. Because in some figures, you might have all states are accept state, if there is, the minimal conditions. We say that a DFA-M, which consists of Q, sigma, delta, Q naught, and F, accept a string if a string at state Q naught. If starting at state Q naught, the DFA ends at an accept state on reading the string W. So we said that we have a deterministic finite automata. If we have a starting state, we have accept state, and the string will fulfill the requirement and ends at accept state. The DFA-M accept a language L which belongs to alpha star or sigma star if every string in L is accepted by M and no more, denoted as L of M. In some books, you will find they said recognizes L, M recognizes L, either accept or recognizes. So both terms in computational theory book, some of them said recognizes, some of them said accepts. So both are valid terms. Is that clear, guys? Okay. So back to next class, we'll have more example in DFA and non-determinism. So we will wrap up what we will have by Friday, what we will have in week 1, 2, and 3. Then assignment 1 will be released next weekend. Determinism versus non-determinism. What do we mean by determinism and non-determinism? given current state Qi, which belongs to Q, and next input symbol X, which belongs to alphabet, the transition function delta of a DFA defines exactly one state Qj that belongs to Q to move to. We call this determinism, which means that with a certain state, I have one option to move to the next state. This is what do we mean by determinism. The next state is determined by the current state and next input symbol. So I'm in a Q node, I receive one, I know where to go. This is the determinism. In graphical terms, this means exactly one arrow comes out of every state for each letter in the alphabet. If I receive 0, I have one option. If I receive 1, I have one option. Same as what we have yesterday. If I receive 0, here. But here, if I receive 1, here. But here, if I receive 0, in this one, to have 1, 0, 1, 0, 0. So I'll go to the state. Okay, non-determinism challenges the idea that there must be a single path to a computation. What if many paths of computation could be followed at the same time? This is the non-determinism. In that sense, non-determinism can be viewed as a kind of parallel computation in which many threads can run concurrently if at least one such thread accepts the computation accepts. A non-deterministic finite automata and FA is like a DFA, except that it's almost similar, except these points. One or more transitions are allowed for each symbol. If I receive 0, I can go here or there. Transition can be made without reading any symbol. So if we read epsilon also, it gives me some other form of transition. However, in DFA, epsilon is not a valid case. The machine accepts if any sequence of choice lead to an accepted state. So if I go this path or I go another path, it will lead to accepted state. Think that we want to go from TEB or from ASEP to Spencer Engineering Building. Either I can go at the end of ASEP where it's behind SEB and use any shortcut between the labs, the concrete labs, and I will move to SEB. Or I can go out, work in Western Road, at the gate, turn right, then turn right to go to SEB. This is another path, and it will lead me to final state because my destination is SEB. Or I can go to outside SEB, go to the left toward the gym, in the circle to left, and then go to SEB. Or go to TEB, to the third floor, use the bridge, and go to SEB. So all these paths, I have different paths. If I want to form this in finite automata, it would be non-deterministic finite automata because I have many paths to arrive at the accepted state. Is that clear, guys?
Hey, Professor.
Yes.
If you had like 0 or 1 took you to your accepted state, is that non-deterministic immediately because both of them would take you there? Or do you have to not know where one is going to take you?
No, you have to be careful. If I'm in current state, Q node, if I receive an input 0, I might go to Q1 or to Q3 because they both will accept 0. So if I have different path to go, then this is a non-deterministic. Give you another example from our real life. When you play like online, each one has the game in his PC working and he's running, but both are connected to the same server and working on the same server, but the server give you one thread to play and give your friend another thread to play.
I don't quite get the second example, but yeah, I think I'm starting to understand.
Yeah, so if I get one, for example, the same example, or let's get another example. So if I said to you, like, we'll have more example now in non-determinism, but if I give you, like, if I get a 0, either it's followed by 1 or 0. So you have two choice. You will have two arrow from that state, right?
Yep.
With the same input, which is 0.
Oh, okay. The following step could take you to
Yeah, the
either
following
place.
step, I can go this route or this route.
Okay, that makes sense. Yeah, thanks.
Is that clear now?
Hmm.
Okay, good. Any other question, guys, before I move on? Okay, so the formal definition of an undeterministic finite automaton is a 5-tuple Q, which is the set of state, a finite set of state, alphabet, sigma, delta, which is the transition function, Q naught, which is the starting state, and F, which belong to Q, which is a set of accepting states. So also one point I want to mention here, we mentioned it before just to make sure, we might have multiple accept state. Starting state is one state, but we can have a multiple accepting state. The main differences in FA relative to DFA pertain to the alphabet and the transition function. So alphabet epsilon equal sigma, the alphabet, union with epsilon. Recall P of Q, the power set of Q, denote the power set of Q. In other words, the transition function take a state and the symbol or the empty string, and it produce a set of possible next state. So once in non-deterministic, epsilon should be included in the alphabet. In DFA, no. This is one more difference. So let's have this example. If we have giving an undeterministic finite automata that accepts string that end in 0, 1. So here we have the language or the sigma consists of 0 and 1, right? And we need that the number or the string should end in 0 or 1. So I'm in a Q note. At the beginning, I will have 0 or 1 because it's end in 2 digits. If it's received 0 or 1, I can stay in a Q note. And then if I receive a 0, I'll move to Q1. And then if I receive 1, I will go to Q2. Formally, how we define that we have a 3-state Q naught, Q1, Q2. This is the big Q. And the alphabet, which is 0 and 1. Then the delta, then Q naught, and the accepted state is a Q2, where delta, the transition function, normally we call it a transition table. So in a Q naught, if I receive a 0, I'll stay to Q naught or go to Q1. If I receive 1, I will stay in Q naught. In Q1, if I move to Q1, I have any path. This one represent whatever the symbols before the last 2 digits, I don't care. Once I reach to the last 2 digits, if I receive 0, I'll move to Q1. If I receive 1, I'll move to Q2, which is the accepted state. Here, whatever at the left side of the last 2 digits, it will be still accepted by Q naught. So then if I receive 1, I'll go to Q2, which is the accepted state. If I'm in Q2, I will receive nothing because the string at that time should be done and all letters in that string or all digits were being read. Why we call it non-deterministic? Because any 0 or 1 before that, I don't care about it. So I have two options. If it's the last two digit, I have to move here. But if it's before, I have to stay here. So I have two possibilities if I receive 0. Because there is a condition, I have to check. Is those are the last two digits? Yes, I have to go this route. No, I have to stay here. So I have two routes for the same input. Okay, look at the NFA computation path giving a string 00101. So if I receive 00101, this is a state. If I have received 00, I'll go to dead. If I receive 0010, I'm go to dead. If I receive 001, then 01, I'll go to Q2. 01, Q2. So I have, this is the end state. And in Q naught, zero, zero, one, zero, one. Here, I believe it should be Q2 also. Since the thread accepts the computation accepts. So here we are in non-deterministic, we define the thread processing, which is the parallel processing, that I have two tasks that process at the same time.
Sir, I have a quick question regarding that. If
Yes.
we can go back. So the top line is all Q0. So how does that work? I mean, if you just have Q0 on its own, then
Yeah, here it's showing you that he defined the nodes or the states. If it's in the first layer, it is for a level Q0, then here a level Q1, then here a level Q2.
right, but the other, so the
You can't
top
call
line.
it A, B, C, D. There is no rule how to name it.
No, my question is, what does that? What are the restrictions do we have? Since if we are able to use Q0 and have a thread going from Q0 to itself to get the actual input string accepted, how does that work? Like, what are the restrictions that we have to actually not use this?
I know.
So if we just follow the top line, like Q0, 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 we get the input string as valid.
Yeah, I mentioned that. I said this should be Q2 and accept the state. I mentioned that.
Right, but why does it need to be Q2 if it's using Q0 beforehand as well? It's just constantly using Q0. It's not following any of the rules as it would.
I told you the name, what you name the state. Here in this example, they use the level. Each state in a level will use the same name. So here we have the level Q0, the level Q1, the level Q2.
Okay.
You can call it A, B, C, D, E, F, G, H, whatever you want, or A1, 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 B1, B1, whatever you want. There is no rule to name the states.
So is the level 1 valid? Like, because on the diagram, the final state isn't accepted as Q0
right?
at the end.
And here he should put this Q0 as accepted state. It's a typos. Because this fulfills the requirement 00101.
So my question is, can we have that Q0 as a final state
Yes.
as well?
Yeah, it's a typo. It should be final state.
So if that's the final state, wouldn't every single Q0 be a final state as well?
No. Is this Q2 final state?
No.
And this is yes. So not if I choose one of the Q0.
Also, the behavior of the final state is different than the finite automator.
Here he named the states based on the layer.
Okay,
Layer 0,
so-
layer 1, layer 2.
Okay, I understand. So it's the behavior of the final state is different. Okay.
Yes. So the accept state is different, whatever you name it.
Okay, I understand.
Yeah. Okay, given an FA that accept all string that contain string 101011. So whatever here before, if I have 11010, which is the final state, and whatever behind it, that would be. Question: what is the role, purpose of the loop transition in Q0 and the Q5? How would the language the machine recognizes change if you omitted either of them? So this is in a class practice. You have to find the answer. And I will add it to the Google Sheet for week 2. Okay? So again, just not to forget, slide 29. Question. Example 2. Recall the equivalent DFA. This is deterministic finite automaton. Notice the NFA was much easier to write and read. Because here, whatever before, whatever after, and for this one, we read it. But if we use DFA, it is more difficult. So in this case, if you are searching for a partial string, it is better now, as of now, we know that to use non-deterministic finite automata. However, I can solve it in a deterministic, but the non-deterministic would be easier. And the state diagram would be easier than the deterministic one. Okay. In fact, giving any string S or W, A1, A2, A3 to AN, and alphabet sigma, the NFA that accept all string contain S is start. As I told you, this is again, if in the exam you see a diagram without the start, this arrow means the start. And sometimes it come like diagonal, depends on the diagram shape. Sometimes we make the diagram upside down due to the size of page in the exam. So this arrow, the first arrow means the start, even if I didn't put it start. Or in the assignment. Okay, so the first state, you see here, the one who asked, sometimes we no need to name the states. Just mention the start and the accept state, and no need to name the state. However, I can call them Q0, Q1, Q2, Qn, or Qi, or here N, Qn. You can call it Qa, Qb, Qc, whatever you need. Okay, and here AI belongs to alpha. So it could be A1, A2, A3, A4 till AN. If I receive A1, I'll move to A2, to A3, to AN, and AI belong to alpha, which is the final state. So any string would be accepted, whatever the letter.
Sir, can I ask a quick question regarding, so the reason why we do not show the external information is because there is multiple different threads happening at the same time for like level 2, level 3, and they go dead, right?
Yes.
And but on the background there is multiple iterations happening, and the only reason why the NFA is easy to read is because we don't have to show those iterations. It is just to show the whole string as it would behave in the accepted method. Is that right?
No. Here, either I will receive 0 or 1.
Yes.
Here, I will receive either 0 or 1. And this is the computation path. It's not the DFA itself. This is a computation path if we input this string. So we know the input, which is 0, 0. The second one is 0, then 1, 0, 1.
No, what I'm saying is the reason why we don't show the whole thing is because we don't
Yeah,
need
yeah,
to.
yeah. We didn't show the whole thing. It's just an example to show you that we have many paths. That's it.
Okay. All right. So
It's not the full diagram.
when we explain the question, like answer the question, do we have to show the paths or?
For
No.
example, if I said to you, like, if we have the following string, draw a sample diagram that shows some possible paths,
Okay.
not all paths.
Yeah, because with the A1 to AN, that would be infinite paths, right? Like an amount of paths. So. Okay.
Okay, the epsilon transition. An NFA can make a transition without receiving any input. This is the difference, also another difference, as I told you, between DFA and NFA. So the epsilon, sometimes I use it as a kind of input. This transition called epsilon transition can sometimes greatly simplify the design. How? Using epsilon transition, given a non-deterministic finite automata that recognizes the set of strings that end in ing or er for an alphabet from A to Z. So whatever here, epsilon, because I have two paths, because I will check either er or ing. So I will check here the last three digits. Do I reach to the last three digits, whatever A to Z before? Then I will move me to N and to G, which is accept state. Here, by default, for your question, if I receive an I, then D, I'll go to the state, but I no need to write it. Okay? And if I check the last two digits at the same time, I will see if it's to E or R, whatever the letters before that in that word. Can you solve a question step by step similar to that? This one will happen in the tutorial, Ahmed. The TA will go step by step. And we'll have, I told you, next class, we will have more and more examples in this. And we will solve examples. Here, I'm explaining the concepts. Then it will be followed for fully class of example for DFA and NFA. No worries. And also in the tutorial, the TA will, I'll give him some another extra examples and he will solve it step by step. But in today's class, there is no time. We need to finish the handout. And next class, we'll solve example about both deterministic and non-deterministic. So don't worry, everything will be clear, Ahmed. Non-determinism, two interpretations. There are two equivalent ways of thinking about non-determinism. Parallel computation, the computation proceeds along all possible paths concurrently. And lucky guess, the computation proceeds along one path only, but always pick the path that leads to an accepting state, if such path exists. And this, you know, it uses sometimes a kind of searching algorithm. Hello, can you hear me, guys?
Welcome,
Yeah, we can hear you.
Yeah, I'm not sure what's happened to my router here. You see my screen now, right?
Yeah, we can see your screen now.
Okay. Okay, and it's the lucky guess. So, as I mentioned before, that you studied in data structure and operating system, how many algorithm that will lead to a shortest path, fastest path. So, but in computation, we call it the lucky guess. So we leave the processor to choose which path it will go. But it should be an accepted state. Is that clear, guys? Okay, we're almost an hour of our class. We'll have 5 or 10 minutes break you need. Guys,
It's up to you.
up to me. No, you guess.
10. I will say 10.
Okay. Okay, we'll go for 10 minutes. We'll break and pause for 10 minutes, then we'll be back. So like 9:35, we will be back. Okay, we're back to recording. So if their number is high, so I'll create a new groups and put them together. And most of the groups, they are full with 6 or 5 students. I will not add to those. And no worries, no worries. We can manage that. I can merge them in 3 groups and we'll have them all together. Unless there are some group, but they are, I don't know, they're not finally agreed or waiting some time. So we'll give them till Tuesday. We'll give them till Tuesday. After that, I will put the student randomly. Why can't we have A to Z straight from the start? This will be a deterministic finite automata. The student who asked this. So wait, now we will prove that we can use either as a deterministic or non-deterministic. Okay, so let's back to our class. So you see the handout, right, guys? You see this, the week 3 handout, right?
Yeah, I see it.
Okay. Okay, we'll continue on non-determinism. So equivalence of non-deterministic finite automatas and deterministic finite automata. A natural question each one of you would ask, how DFAs and NFAs are related? In first glance, it seems like NFAs can do more, but is this really the case? So the first step to answer this question is to ask, given a DFA, does there exist an NFA? By equivalent, we mean that they accept the same language. So these are some questions that might come in your mind. So the first theorem that we will have, all DFAs have an equivalent NFA. Every deterministic finite automata has an equivalent non-deterministic finite automata. How we can prove this theorem? Proof is by definition. Every DFA is also an NFA. It just shaping that DFAs do not make the use of extra power of NFAs, which is multiple transition for the same state for the same input and epsilon transition. It cannot make the epsilon transition. So these give more power to NFA over DFA. So each DFA is an NFA. Now, comes to the harder part. Prove that every NFA has an equivalent DFA or not. If every NFA has an equivalent DFA, then NFAs is ultimately have no more computational power than DFAs. Theorem number 2, all NFAs have an equivalent DFA. Every non-deterministic finite automata has an equivalent deterministic finite automata. But the figure will be more complicated. Proof: to show an FA has an equivalent DFA, it would be sufficient to prove the existence of a general algorithm to convert any NFA into an equivalent DFA. How we will convert that? We begin by reviewing each component of definition of a DFA to see what need to be adjusted. States. The first thing to consider is the finite set of states. In an NFA, the computation can be in combination of states at the same time. In a DFA, it can only be in one state at any time. Idea: let set states in an NFA each be a single state in corresponding DFA. So if we have a branch, we'll make it a single set in the DFA. Suppose an NFA transition to state Q0 and Q1. In our corresponding DFA, we can define an amalgamated or unified state Q0 and Q1. How many such states do we need? If our NFA has a Qn equal k of length the cardinality states, our DFA has a QD, which is the power set of Q of n, which is 2 to the length to the power of length of Qn. Example: Qn is Q0, Q1, Q2, then Qd equal phi, Q0, Q1, Q2, Q0, Q1, Q0, Q2, Q1, Q2, Q0, Q1, Q2, where phi is dead state, which we will omit for notational clarity. This is the complete set of states that our DFA could possibility use. Of course, as we fill in the transition table, we may find some most states goes unused. Alphabet, the alphabet says the same. Sigma n equals sigma d, doesn't change. Starting state Q0 belongs to Qn. The starting state of our NFA, the starting state of the corresponding DFA is a Q0 union the delta, which is a Q0 and epsilon. Combination of Q0 and any other state reachable from Q0 be an E transition. Final state, let Fn be the set of final state of our NFA. Recall the NFA accept if any of the computational path accept. Taking this over a DFA means designating any of the amalgamated states as accept if they contain some Qi belong to Fn. Example: if Fn equal Q1, then Fd Q1, Q1, Q0, Q1, Q2, Q0, Q1, Q2. Filling the transition function. Guys, these are definitions. Next class we'll have a full example. You will understand everything. So no worries. Filling in the transition function delta D proceed in two parts. Part 1, we write a table with a single state of 4 rows and letters 4 columns. We use the NFA's transition function delta n to fill this table, converting set of state to amalgamated states, but we still have to account for epsilon transition. The way we do this is follows. If we transition from state Qi to state Qj, and the Qj contains an epsilon transition to state Qk, then in effect Qi transition to Qi union Qk. This continues recursively until there are no new epsilon transition to follow. How we will do that in the example will be clear. Transition function continued, part 2. Now that we have the transition for the single state written, we add new rows to the table corresponding to the amalgamated states Q0, Q1, Q0, Q2, etc. We fill in these cells by taking the union of the cells of the corresponding single state. For example, to fill in the cells delta D, Q0, Q1, and A, we take QD, Q0, A, union QD, Q1, A. we will see all of these things, we will do it, and it will be clear. But this is a theoretical part that I have to deliver. But in the practical, when we have a hands-on example, all of these writing will be like easy for you, and you understand it by remembering how we solve the questions. The simple example, first example today, convert the following NFA to an equivalent DFA. We have start 1, 2, and 3. If we receive B, we'll go to 2. If we receive epsilon, we'll go to 3. Then if we receive A, we'll go to B, to 1. And if we receive A and 2, we'll stay in the same state. And either if we receive A or B, we'll go to 3. And the Q naught, the starting state, is the final and accepted state. So example 1, state QD will be end by using some subset of the power set Qn. Example, QD belong to the P of Q of n. Alphabet are A and B. Start state is 1, but there is an E transition to 3. So the DFA start state, therefore, is the amalgamated state 1 and 3. So if there is an epsilon, so it could be A or a 1 or a 3. Because what do we mean by E transition? If I didn't receive any input, also I will move to 3. So starting point could be 1 or 3. Final state is 1. So FD is the set of all amalgamated states that include 1. For example, 1, 1, 2, 1, 3, 1, 2, 3. Transition function, if I receive 1, I'll move to 2 if I receive B. But if I receive A, nothing happened. In 2, if I receive A, I will state in 2. If I receive either A or B, I'll move to 3. So 2 or 3 and 3. And in 3, if I receive A, I'll go to 1 or 3. This is in part 1. In part 2, transition function continued. Now we fill the rest of the amalgamated states by taking the unions of the single states. We continue. If we start at 23, here are the other one for the epsilon transition. Guys, next class, I will use the pen pad, and I'll explain step by step for you in the class, so it would be clearer for you. Minimization, we are using more states than we need. If you look down the column, you will notice that no current state symbol combination will lead to state 1 or 1, 2. Since neither of these states are start state, we can never reach them, so we can eliminate them. And here will be the DFA. As I told you, the NFA are simpler, but if we convert it to DFA, any NFA has equivalent DFA, but it will be more complicated. So this is based on the transition function. We will have the following DFA like this. Next class, we will solve this example and another example in a step-by-step manner, so it would be clearer for you guys. Equivalence of DFAs and NFAs. What does this mean? We'll recall we proved by definition that all DFAs have an equivalent NFA. Then we demonstrated an algorithm showing all NFAs can be converted into an equivalent DFA. NFAs have no more computational power than DFAs. In fact, the set of language recognized by any DFA and NFA are equivalent. And we call them the regular language. Remember this term, regular language. Next handouts, we will start talking about regular and irregular languages. Okay? That's what we have for today. Next class, which will be Thursday at 3:30, which is the tutorial class, we will start solving examples that will clarify anything and how to solve a question. This will give us the chance to solve assignment 1 question. I'm not sure to put handout 4 as part of assignment 1. I'm not sure yet, but once we finish the tutorial next week, the class that we'll have it in tutorial, then I think assignment 1 will be released. You will have 10 to 12 days to solve the assignment and submit your assignment as a group. However, in Wednesday, I will finalize all the groups. So on Thursday class, everybody will know their group. And the same term paper group will be the assignment group. In the instruction, 1 submission, 1 guy who will be the focal point in OWL, and he's responsible to submit the assignment in OWL. If a group make 2 submissions, this will lead to a problem to the TA. So each group, you have to choose 1 member. After we finalize all the groups next Wednesday, each group should choose 1 member, and this member will be the one who will submit in OWL, whatever, for the term paper, project, presentation, or assignments. Is that clear, guys? I know today, this handout is a bit, that's why normally I give it very quick, but we'll have all the info here, how we do the algorithm, how we will convert in step-by-step manner examples next class. So you will have a full set of examples for deterministic, non-deterministic, how we convert between deterministic and deterministic. So any ambiguous, any confusion you have, it will be clarified next class with examples. Any other comments, guys, before we leave or stop?
I had a small question. Can you hear me? So I'm just like wanting to clarify the difference between a DFA and an NFA. So DFA or an NFA, you can have like 2 states at once, and you can have like multiple inputs that like lead to the same state. Well, DFA is kind of more rigid.
Or
that-
sorry for interrupt you, or 1 input can lead to either one of 2 states.
Okay, yeah. So a DFA is kind of more like linear in terms of like you get 1 input, it's 1 state.
Yes, that's why the DFA diagrams are more complicated than the NFA. NFA is more generic.
Okay, thank you.
You're welcome. Okay, let me see here. Of course, some chat are coming in private. I don't want everybody to see. Is there a scenario where you would want to do this way, though it seems more complicated? Will you record tutorial session? Yes, I will record tutorial session. If you cannot attend it, you can see the full recording. Also, guys, I don't know. For example, the attendees today start with 53, then now 47. Maybe some people leave right now, which is almost 30% of the class. Yesterday, I know that it's 8:30 in the morning is a bit difficult for some, but however, even in the YouTube channel, I'm not seeing the students, they are watching the videos. I'll send an announcement on that, but at the end point, it's back to them. Those who will not attend and depend only on the handout and the class notes will not be enough for them, I'm sure. Last year, they did the same and they get a very bad mark. And at the end of term, oh, we need a good mark, what to do? Can I do an extra assignment? No. From the beginning, I told everybody, if you attend all the classes or watch all the classes, whatever, come to the office hour if you have a question, attend the tutorials, solve your assignment by yourself and understand. For example, in assignment, if I bring 6 questions and you are 6 people, each one will solve 1 question. But that doesn't mean that you do not have to see how the other questions are solved and understand it, not just to see. You have to understand how the assignment is solved. Because in the quiz, when I ask you a question on the term paper, this would maybe get a bad impact about you because you don't understand. So this course depends on understanding, not memorizing. Yeah, I know that some of them, they said I subscribe. Yeah, I'm not looking for subscription. I'm not a YouTuber, but this, because I compare between the number of subscriber and the number of views for each video, the same people who attend the class, the same people who watch that video. This is my point. We have 151 student and we have 40 subscriber and each video between 50 to 60 views. I don't know. Yeah, today I will upload both today class and yesterday class. No worries. No
I
worries.
think like just as a comment for myself, like I think you are preaching to the choir a little bit to us because you know we see the importance of coming to your lectures. Like the people who are here, and you know I enjoy your lectures and I am getting a lot of information out of it. So thank you for that. And it sucks that other people don't. But I don't know. I think those students are going to figure it out sooner or later that, you know, not coming to class and not attending and not watching the videos is going to
Yeah,
blow
this
up
is
in
my
their
point.
face.
This is
But
my point. Yeah. Thank you, Rachel. Thank you. I appreciate your attendance and all your colleague attendance. And I start feel because I look to the names for who attend, they are almost the same people. So the others, they will leave it to the assignment day or to the quiz day. I will see on that day that the number of views jump. But this amount of videos and this amount of hours, how you can catch it in 1 or 2 days. This is my point. I'm worried about them because always I'm worried about my students. I wish to my student all the best. You know, some kind of instructor, they don't care. There are very few in the world, but as a university professor, I care about my student and I wanted them to get the information in time so they will not suffer prior the assignment submission time or exam time. And one of those, if he's a member of a group and he cannot solve that question that assigned to him, or he cannot do his part in term paper, this will affect the whole group. So I'm trying to encourage everybody to do it in time so all people can get high marks, all people can benefit from the course. This is my point. But at the end, it's their call. I cannot enforce anybody. They are, you know, adult and they know what they have to do. Thank you, guys. See you next Thursday. If you have any question, don't hesitate to join the office hour in every Wednesday from 4 to 5 p.m. And if this time not suit you, just pop me an email and we can arrange for any other suitable time for you. I'm open to answer any question.
Sir, I have a quick
Yeah.
question before we end. When are we going to have the tutorial, since the tutorial hours would be the class hours? So when can we ask the TA for the explanations?
The tutorial towards next week and the week after, it will be delivered by me. It's not tutorial, it's normal class.
No, I know.
Yeah,
my
but
question
in
is,
tutorial, normally I give him some few questions to solve. And also he will bring his own question because he knows the material, he has access to all things. And this is the second year he TA the course. He's aware about everything. And almost his examples and solution will take almost an hour of the tutorial. The another hour will be open for a question from the student. For example, in assignment question 4, we are confused about this. Sometimes maybe you don't have a question, but you will benefit from your colleagues' question and answers.
my question was, when are we going to have the tutorial?
I told you, for example, if I release assignment 1, let's say next Thursday after class, and the deadline will be Monday, not the after. So it's almost 12 days. So the other Thursday will be the tutorial. Normally, the tutorial is scheduled to be before the Monday and Thursday, before the Monday, which is the deadline. Did you get the
That's
point?
what I understand that, but as you said, the two courses, like the two tutorial sections will be the actual course lectures
Yeah,
for the
I
next 2
said,
weeks. So
I said this is maybe change. So if I release the assignment one next week on Thursday, then the next tutorial will be a normal tutorial session, and we will do the class the week after.
okay, I understand.
So I will not make any conflict between, no worries. Because the tutorial before the assignment submission is very important. Normally last year it was very beneficial for the student and they got good marks in the assignments.
Okay, I understand.
Any other question, guys?
Hey, Professor. I have a few course questions. They're really short and minor. In week 2, if you could, like, I don't know if you could screen share week 2 right now.
Yes. This is 3. Let me open 2.
All right. So in slide 33, so I think it's like towards the end.
Yes.
Yeah. So in this slide, you said that like, we didn't include dead states, right? Because if you get like, let's say you get any string from A to Z, and then you do, and then you get I, and then you get D. You said we wouldn't draw dead states because that would be, I don't know, too complicated.
Yeah, because in dead state normally we use it with DFA. With deterministic
okay.
finite automator. We replace that in epsilon. So we can put here if it's no epsilon and it will stuck here, which will be infinite loop, which is the same concept as dead state.
Okay.
But I try to, Dr. Essex tried to simplify the figure as much as he can. Because, we do not go in very deep details to do graph. This graph, if I'll go in every single detail, we might have another 4 or 5 states, which will make it more complicated.
Okay. I also have another question about slide 28, like the example 1, if you scroll up just a little bit.
28 or 20?
28. Yeah, that one just now. So, sorry, this is a silly question, but is 00101, are we expecting that string to be at the end of the input or just any time inside the input?
Yeah,
if that makes sense.
He said it's a comprehensive exam. So he said, look at the NFA computation path, given input starting string 00101, which is 00101. Okay.
Okay.
So this is a part of a full diagram. It's a part of a DFA diagram. And if we given that, check this input is an accepted state or not within this NFA. So if you look here, it should be accept. Q naught here should be accept. And this path here, he put this example and he didn't put the Q naught as final state. If you see here about when he talk about lucky. So the computation proceed along one path only, but always pick the path that leads to an accepting state if such a path exists. So here, even this one lead to a correct path and accept path, but there are another path if it's reached to end, which means there is another path that will lead you to accept the state. This what does he mean? Because these at the top surface level, we don't go in deep details. It's part of diagram that's showing you that we can go in different paths.
Okay, so then the first two
some path will lead you to dead.
Oh, okay. So they're just representing like the different possibilities of maybe going to a dead state, but we're not writing it down all of them.
Yeah, this is what they mean in the diagram. And how they name the states, they name them based on the layer. Not each state has a queue, not Q1, Q2, Q3. And you see, in some example, we leave it empty. We don't put anything inside it.
I see. I see.
If you see here, we leave it empty. We don't put numbers. All are possible thing to solve your question. Here, we don't put. We put the input, but we didn't give it name. But we know this is a part of the big queue, which is the set of states.
Yeah. Okay. Okay. I was just a bit confused because like I wasn't sure like what those other routes were doing, but it's just to represent alternative like input strings. Okay.
Just to show you that we might have different threads. In parallel computing, no, each thread will lead you to accept a state. However, in lucky case, there is one accept state, and how much lucky you follow that pathway, you will reach to accept the state.
Okay.
Any other
All right.
Yeah. Any other question, guys? Those who don't have a question, you can leave. See you next week. Have a nice weekend.
Have a good weekend, sir.
You too. Shall I stop recording? I'll stop recording.